Hello APC Mechanics students, today we'll solve the past paper FRQ 2022 set 2 exercise number 3. And always remember that the figure appears above the text, so you always look at the figure above and not below. A uniform board of length L, the moment they mention it's uniform, which means the mass distribution is the same and the center of mass is located geometrically at the center of the rod or the board. Of length L and mass M is attached to a pivot which is L over 4 from the left end of the board. The left end of the board is attached to an ideal spring. The spring is ideal, which means we can apply Which law? Hooke's law of spring constant K that is attached to the ground. The right end of the board is initially held by students so that the spring is unstretched. As shown in figure 1, the student slowly lowers and then releases the board. The board remains at rest in the horizontal position when the spring is stretched. As shown in figure 2, the rotational inertia of the board above the pivot is I. So we don't need to worry much about the parallel axis theorem because already the rotational inertia is given around the pivot itself and not the center of mass. In part A, they're telling us on the rectangle below, which represents the board, draw and label the forces, not components, that act on the board while the board spring system is in equilibrium. Each force should be represented by an arrow that starts on and points away from the board and should represent the location at which that force acts, which means a rigid body diagram and not an FED. Basically, we need to do the rigid body diagram for the figure 2. Now, what are the forces acting on the board? We have, remember that the pull of gravity would be acting at the center of mass. We have F at the axle, and we have the force provided by the spring, which is basically downward to balance the pull of gravity. Now here, if you notice carefully, they have divided the board for us. So if this is of total length L, then each segment would represent L over 4, then basically the pivot would be here and the center of mass here. So we have the pull of gravity at the center of mass. And we have the force provided by the spring. Then let me say this is F due to the tension. And the force at the axle or the force at the pivot would be represented by that. Now, because they're mentioning, first of all, they didn't mention anything about the relative length about the forces, but already I have taken that into consideration. Notice that I have represented this force to be equal in magnitude to this force because they provide balanced torques, as this provides no torque. However, also because forces up should be equal to forces down, I have represented this to be the double of these. Now let's move on to the next question. In part B, they're telling us derive an expression for the distance the spring stretches delta x when the board is in equilibrium. Express your answer in terms of K, L, M, and physical constants as appropriate. So it is at equilibrium, which means torque net is equal to 0. Now, what are the forces that are providing the torque? We have only the force due to the tension and the force due to the gravity because this provides no torque. So instead of writing torque net is equal to 0, we can directly say that the torque provided by the tension should be equal to the torque provided by gravity, and the reason here is given by balanced torques. Now both forces in this configuration are being applied tangentially. Why this is important? Because remember, the torque is a force times distance times cosine of the angle between the force and the tangential direction, so no need to worry about cosine. Now the force provided by the tension around this pivot would be the tension itself multiplied by L over 4, and the force provided by gravity would be the mass of the rod, which is M, multiplied by G multiplied by L over 4. And indeed, the mass of the rod is being denoted by small l. So let me say the force of the tension multiplied by L over 4 should be equal to mg multiplied by L over 4. Now L over 4 cancels, and the tension force would be equal to K multiplied by delta X, and this is given by Hooke's law. Then K delta X equals to mg, and we're interested in determining delta X. Then in this case, delta X is simply given by the ratio mg divided by K. Okay, now moving on to the next page. They're telling us a student pushes the board down on the right side, stretching the spring a new distance delta x2 from the unstretched position. The board is held at a small angle theta 0 with the horizontal as shown. The student then releases the board from rest. Now what would happen in this case? If the board is given an initial push downward, so we expect from the equilibrium, we expect that the board will start to oscillate around the equilibrium position. And whenever we're talking about oscillation, we know that alpha would be proportional would be proportional to the position, which means that the graphs of omega and alpha should have trigonometric shapes like sine and cosine. Then the sine would be something like that, and the cosine would be something like that. And if we're talking about the magnitude, we can ignore these parts, and we have two shapes, either 1 or 2, and either 2 or 1 here. And this depends on the physics of the system. Okay, at time t equal to 0, the board is released. At time t is equal to t1, the board first crosses the horizontal. Sketch a graph of the magnitude of the angular acceleration alpha of the board as function of time t from time t is equal to 0 to time t is equal to t1. So if you think about it, we need to plot alpha. One way to do it is to understand that at this point, starting from t is equal to 0, and that would be t is equal to 1 when the board passes through the equilibrium. Here the acceleration is maximum and here is minimum. So for this reason, the graph of alpha would be something like this. This is one way. Another way is to think about it. If you determine omega, then you would be able to plot alpha. Now here in this case, omega will be starting from rest. So the shape of omega would be something like this. If omega is like that, then alpha would be like this, okay? Because they should be complementary for each other. So now after we have understood this, the shape of alpha, and remember that the angular acceleration through the equilibrium position is always 0. Now the shape of alpha would be something like that. Which is a part of a trigonometric function concave downward. Okay, let me draw it more perfectly. So it should end at 0 and start at a non-zero value, and it's going down, decreasing. Then this is it for part C idea 1. Now C idea 2, derive an expression for the angular acceleration alpha 0 of the board immediately after the board is released. Express your answer in terms of K, L, M, I, delta x2, theta 0, and physical constants as appropriate. And we know that in such type of problems, always and forever, to determine the angular acceleration alpha 0, this is done by utilizing Newton's second law. And because this is a big law, we need to state apply Newton's second law. It's not much important whether we state for rotation or for translation, and it's given by tau naught is equal to I multiplied by alpha. Here I is for the board, but let's double check that there is no any other object that includes moment of inertia, and indeed the only massive object is the inertia of the board, and the spring provides no inertia. Now, what are the forces that produce torque? We have the torque due to gravity, we have the torque due to the pivot, and we have the torque due to the tension. All of these would be equal to I alpha 0. We need to use the same notation. Why they have specifically or stated that this is alpha 0? Because from the previous graph, we know that alpha is not constant, it will vary. So at different instant, we expect different values for alpha 0. Now we can directly eliminate this because the reaction or the force at the pivot passes through the axis of rotation. And now we need to determine the torque produced by each force. Then let's get back to the figure. Now here it's a bit tricky. We need to draw the forces. So basically, let me start by the pull of gravity. The pull of gravity at the center of mass, it's pointing downward. So that's the pull of gravity, which is basically given by mg. Now that would be the radial direction, and that would be the tangential direction. Now if you consider another horizontal here passing through the point of application of the force, that would be the angle theta 0, because this is a horizontal and this is a horizontal, so this is theta 0 and this is theta 0. But notice that this is radial and this is tangential, so that they are perpendicular. That would be pi by 2 minus theta 0. And because this is horizontal and this is vertical, again this is theta 0. And now what does the torque states? The torque states it's the force times the distance times cosine of the angle between the force and the tangential direction, which is given by cosine theta 0 basically. And we're assuming that the positive direction is anti-clockwise, so that would be negative. So here we can safely say that the torque provided by the pull of gravity is given by minus mg times the distance, which is L over 4 multiplied by cosine theta 0. Now what about the torque provided by the tension? Again, we need to refer to the figure. So basically that's the radial direction, that's the tangential direction, and that's the force provided by the tension. Now if this is a horizontal, again we can do here a horizontal. Now if this is the angle theta 0, then that would be again angle theta 0. And because basically this is horizontal and this is horizontal and this is a line joining them, so this is theta 0, then that would be pi by 2 minus theta 0 for the same reason. Let me explain it again. This is radial, this is tangential, so they are perpendicular. Again, this is horizontal, this is vertical. If this is pi by 2 minus theta 0, then this is theta 0. Then we're projecting ft along the tangential, that would be cosine theta 0. So here we would have plus, because it's providing torque in the positive direction, tension multiplied by L over 4 multiplied by cosine theta 0 is equal to I alpha 0. Okay, so mg is okay, L is okay, theta 0 is okay, the only I is okay, but now we need to play with the tension. Notice that the elongation of the spring in this case is given by delta x2, because if you read the text carefully, a student pushes the board down on the right side, stretching the spring a new distance delta x0. So delta x0 represents the total elongation and not part of the elongation, because initially the elongation was given by delta x in the equilibrium. So now the total elongation is given by delta x2. So we can say that that would be minus, so let me write here, minus mg L over 4 cosine theta 0 plus k delta x2 multiplied by L over 4 cosine theta 0 is equal to I alpha 0. Now we're interested in alpha 0. Then alpha 0 in this case now everything is divided by 4 and it's divided by I as well, so we can open a big fraction. In the denominator we have 4i, we can factor out L. And in the numerator we have k delta x2 theta 0. Okay, we can also factor out cosine theta 0 minus mg multiplied by L cosine theta 0, and that would be the expression of the angular acceleration alpha 0. Okay, immediately after the board is released. Now the final part D, two blocks of equal mass m are attached to the board, equal distances from the pivot point as shown. Then we have added these two masses. The board is again pushed down on the right side so that the spring stretches the same distance delta x2 as in part C. The board is then released. How does the new angular acceleration alpha prime on the blocks are attached compared to the angular acceleration alpha 0 from part C? Now the thing is that there is no penalty of trying your luck and choosing one of the answers, okay? But here in this case, because we have done something to the system, trying to avoid, or it's not necessary, it might be alpha prime is equal to alpha 0. The thing is that this is very tricky, Now these two blocks, they provide torque for the board, but they are at equal distances. So without going deep into the geometry, if the board is being horizontally aligned and the two blocks are here, so they provide equal torques. So basically the net torque on the system didn't change, but we know that according to Newton's second law, alpha is given by the torque net divided by the rotational inertia. So alpha is not being affected only by the torque net, it's also affected by the inertia, and inertia have been injected for the system because we know that for a particle or a block around a pivot, it has a rotational inertia given by mr squared. For this reason, if you remember, whenever I try to set up this equation, I ask myself, what does I represent? I is the rotational inertia for the system. And I double check that the only body in this system that have inertia is the board. So now the thing is that placing these two blocks won't change the net torque, but inertia has been injected in the system. And because alpha is inversely proportional to inertia, inertia has been increased, which means alpha decreases. So in this case, my choice would go for alpha prime is less than alpha 0. The new acceleration is less than the previous one. And let me state it properly, since the net torque on the system is the same because the additional torques by the blocks balance each other but the total rotational inertia of the system increases and the angular acceleration is inversely proportional to the rotational inertia, which is I. Then, as I increases, alpha decreases. And that's it for me in this video, guys. See you soon in a new one.